I basically
Oh, seriously?
what they put on the thing, I don't know what they say now.
Where have you been all my life? Your name is Gabby?
Yeah,
Okay, cool shit.
I graduated, so
Pardon?
I'll be right Oh, you did it?
Oh, I graduated in 1920. What? Are you gonna miss me? Are you gonna work?
I'm not saying that.
Okay. I'll see you then. Yeah, we can't give you money now.
Oh, yeah, sorry.
Okay, so
You still need this shit.
for the finale of the semester of the seminar series, we're very pleased to have Martin Charles Golumbic visit us. And he's a professor of computer science and director of the Caesarea, the Rothschild Institute for Interdisciplinary Applications to Computer Science. So this is an institute at the University of Haifa, which is interdisciplinary. They're very interested in the applications of computer science to a range of disciplines. And Charles Golumbic has a very impressive bio, and I'm only going to highlight some of the main features. He's the founding editor-in-chief of the journal Annals of Mathematics and Artificial Intelligence. He received his PhD in mathematics from Columbia University in 1975. He's held positions at the Krant Institute of Mathematical Sciences of New York University, at the Bell Labs, at the IBM Israel Scientific Center, and Bar-Ilan University. And he also has a pretty impressive list of worldwide universities that he's been a visiting professor at. He's the author of the book Algorithmic Graph Theory and Perfect Graphs, co-author of the book Tolerance Graphs, and his most recent book is Fighting Terror Online, the Convergence of Security Technology and the Law. Golumbic was elected as Foundation Fellow of the Institute of Combinatorics and its Applications in 1995. He's been a Fellow of the European Artificial Intelligence Society and a member of the Academia Europaea Honors Causa, elected in 2013. So this gives you a sense of his different areas of expertise. His current area of research is in combinatorial mathematics, interacting with real-world problems in computer science and artificial intelligence. And I'm looking forward to hearing about the perspective of reasoning about time. Thank you.
Thank you very much. It's nice to see a full room. How many of you do not have a PhD yet? Good, because I'm talking to you. When I was your age, I didn't have a PhD either. But I don't think I even knew the difference between Floyd Warshall or Dijkstra or Kruskal's algorithm, but you probably all took Professor Schwartz's class, so you know about those algorithms. You might need a little bit in terms of understanding a few of the details of this talk, and but nothing really more than that except an open mind. I'll talk about temporal reasoning, and just want to tell you that temporal reasoning is a very old science, about as old as the dinosaurs. Well, not exactly. These look like the characters I saw at Disney last week. But reasoning about time has to do with this paleontologist who is thinking, as he's looking at this skeleton, and he's thinking, okay, what did this actually look like? And he uses various scientific experience that he has, and he's thinking, well, maybe this set of bones looked like this dinosaur, or this, or this, or this. Various possibilities. He has clues from the size of the bones. He has clues from his knowledge about dinosaurs, and he's trying to put together some kind of reasonable, plausible picture of what the dinosaur might have looked at. We're going to do that somewhat in our investigation here. In talking about reasoning about time, I'm going to look at sort of two sides of the world. One will be a constraint-based scheduling application, for example, and the other will be qualitative relations between time intervals. Let me show you an example of what I'm talking about. In constraint-based scheduling, we're talking about temporal events, say intervals on the line, lecture A, lecture B, lecture C, and we know something about their duration. In fact, we know from the timetable exactly that lecture C is supposed to be from 11 a.m. till 1400, which is 2 p.m. And that this lecture E is a shorter lecture, and it happens to be between, looks like 12 and 1:15. And these are inputs to us, and in this particular scheduling question, you might ask, how many classrooms do I need to satisfy the assignment of classrooms for these lectures? In the qualitative world, instead of having exact time points for when a temporal event starts and finishes, here we have information about time intervals, some event, only in terms of what I would call qualitative relations, such as dinosaur S emerged before dinosaur T and perished not after it. So there's no mention of time points here. All we have is some kind of relationship between these intervals. And this statement, as it might be said in English, can have different scenarios, just like the paleontologist could think of his dinosaurs looking in four different ways. Here, there are four different possible scenarios of how the interval for S and the interval for T might interact. It may be that they are disjoint, that S really perished, and then sometime later T emerged. It could be that S started and some event, catastrophic event happened, and all the S's died out, and the T's began. It could be that they overlapped. It could be that the T's emerged sometime during the point where S is still alive, and they both died off at the same time. These are the four scenarios that are consistent with this sentence that S emerged before T and perished not after it. We would like, in problems like this, to be able to come up and say whether this statement is consistent and in what ways it might actually be realized. Maybe I'll say, no, I think I can say. So in that example, we have our paleontologist who wants to determine, in this case, the relative span of existence of a particular kind of species. We'll call them B for Brontosaurus, P, S, and T. And his assumptions are the partial information that he gets about the position of their intervals on the timeline. So let's look at this an example here. If I were to give you the information that B and P did not exist simultaneously, well, that would be translated into either B is disjoint and before P, or P is disjoint and before B. Those are the two possibilities. No other sort of possibilities express that phrase in English. If I were to say that P perished before S emerged, then I would have resolved that ambiguity from the first one. If I were to say that P, well, here I have S, P perished before S emerged, and I know that this is the only scenario in which their intervals could have been placed on the timeline. If I were to be told that S emerged before T and perished not after it, that's like what we saw in the first example, I have 4 possible scenarios. And if I were to tell you also that either P perished before T emerged or P emerged when T perished, then I would have either this scenario that P is disjoint and precedes T, or that T precedes P and the finish point of T coincides with the start point of P. Now put those all together. I guess I even have yet another clue here. P emerged before it perished during T's time would be something like this, a containment relationship. So the question that comes up in reasoning problems would be, given all that information, is there a consistent solution, or is there some contradiction? So, is there a scenario satisfying all of those assumptions? I can use this as I move around. So that's another the kind of interval reasoning about time intervals. There are other kinds of temporal reasoning problems. You've seen puzzles like this. My wife likes to do these before she goes to sleep sometimes. You are given some story. It's not important to be able to read the story, but in that story it has different clues. Here's a list of the clues and some information about various journeys that this explorer took that happened during these years, and these products that they were, I guess, carrying and where they went, and you have to find out what really happened given all of these clues. Here's another example of temporal reasoning. News reports. Well, here's some ancient history for you guys. On the 20th anniversary of the Watergate break-in, which you may have read about in history books, Mike Wallace, who's I guess no longer with us either, was said to have claimed the following: that he had eliminated Alexander Haig, who was the Secretary of State at the time, and several other people from being a guy who leaked all this information called Deep Throat. He had eliminated them as possibly being Deep Throat, because nobody knew who Deep Throat was, because he had been abroad on at least one of the dates when Woodward, who was a reporter for the Washington Post, had reported that there was a meeting that took place between them in some garage in Washington. So here is a kind of example of spatial information, I guess London versus Washington, and temporal conflict, because I guess only Hermione can do 2 things at the same time in 2 different places. Here are some other issues in temporal reasoning that we might like to be able to automate. You have a chronology of the story, reporting events in the order in which they happened, temporal information about actions, phrases in your story like something happened 10 years ago, or it happened in a particular year, or it happened at a particular time at midnight. You have temporal clues, such as expressions like before, after, together, with. All of those things give you information about time, which you might want to put together to try to reason about time. Some of the general issues that you would need to consider when you implement a system that has to take time into consideration would be the property of granularity. Are you talking about events being years apart or seconds apart, nanoseconds? If you're a physicist, your granularity of temporal events of some explosion might be different than a historian who was looking at days or even epochs. We have to look at different models, some that talk about points of time, like 6 o'clock, or time intervals, like between 5 o'clock and 6 o'clock. Issues of persistence of a world state, for example, some things that are changing over time don't change their state. They stay in the same state. Once you are dead, you cannot come out of that state, whereas other actions, things will happen and change over time. We also have to deal with partial information, where we don't have all of the information, we only have part of it. What do we do in terms of determining whether what we have is consistent? And the problem of synchronizing timelines. I report, this is what happened this afternoon, and someone else, having seen the same things, reports what has happened this afternoon. And maybe our timelines are not exactly synchronized. How do you map an event that I saw with the same event that someone else saw in terms of our timelines? Here's another example of reasoning about time. Every Monday morning for years at about 11:30, telephone operator in a small Nevada town would call would receive, do you know what a telephone operator is? Do you know what Nevada is? Well, we received a call from a man asking what was the exact time. Hello, Sophie, what time is it now exactly? So one day the operator summed up the nerve to ask why you have this regularity that you every day call me. Well, you see, I'm the foreman at a local sawmill, and every day I have to blow the whistle at noon. So I call you to get the exact time. I said, well, gee, that's really funny, because all this time we've been setting our clock by your whistle. So the kind of causality and lack of independence, not once in a while. So then I went to some of my temporal reasoning friends to ask their opinion about. So I went to Zeno, who was a good buddy of mine, and he mentioned, well, you remember the paradox of the Achilles and the tortoise. Issues like in a race, the quickest runner cannot necessarily take over the slowest runner. Well, that was his paradox, called the arrow paradox. In fact, you can prove that you can't even move. Then I went to Aristotle, and he said, I dispute Zeno's reasoning. Time is not composed of nows, meaning time points. If there is just a collection of nows, then there is no such thing as temporal magnitude. And he wanted to be able to express duration. Heraclitus. I don't have any Greek students here that can pronounce that. Said change, but for them, change is the only constant in the universe. That's a great line. On those who step in the same river, different and different waters flow. Okay. Then I asked a few of my more recent friends, but we don't care about what they said as much as the old Greeks. Okay, but my good friend Alfonso in Brescia said, perhaps the most important accomplishments in the last years are Allen's interval algebra, which I will mention shortly, and Villian and Kautz's point algebra, which I'll also mention, and the Golumbic and Shamir classes, which I'll mention. So I thank him. Let's talk about dinosaurs, but let's talk about the reasoning using intervals without mentioning numbers. Qualitative temporal reasoning. No mention of numbers, clock times, dates. Relations in these models are simply before, during, after, not after, between pairs of events. And the algorithms that are used in this qualitative reasoning are algorithms of propagation of constraints between pairs of events and backtrack search. Propagation of constraints means that I have some constraint and then some other constraint, and somehow one constraint forces another piece of information to follow. And backtrack search, well, that's searching, you come to a dead end, you back up and you try to continue in a different search path. Here's an example of called meets, meets, meets. This is even okay for a reader. Imagine that you have a kind of table of algebraic closure. You'll see what I mean in a minute. Suppose I told you, this is the clues that I give you, that interval 1, or event 1, meets interval 2. Okay, that's illustrated here. I1 meets, touches I2, and then I2 continues. So they intersect, they only touch at one point. And I also tell you that I2 meets I3. What can you derive from that? Sort of like transitivity. Transitivity would mean like if A is less than B and B is less than C, then you conclude that A is less than C. Can you do something similar with intervals? Well, here is exactly that case. That if I meets, I1 meets I2, I2 meets I3, then you can conclude something very strong, which is that I actually is strictly less, that I1 is strictly less than I3. So meets, meets, meets implies some sort of unique extra piece of information that wasn't given to you. So it's a kind of algebra. People look at it like an algebraic rule, that you have a relationship between 1 and 2, a relationship between 2 and 3, and that, therefore, when you combine with the and, gives you another outcome. Let's look at a more complicated example of reasoning about intervals. Call this overlaps, overlaps, overlaps. The same kind of idea. I tell you that 1 overlaps with 2. I tell you that 2 overlaps with 3. What can you tell me then about the relationship between 1 and 3? Well, the answer here will not be unique. Why? Because there are 3 scenarios that I've drawn here that are all consistent with this information. The first one has I1 overlapping 2 here, I2 overlapping 3, but the relationship between 1 and 3 is strict order. That is, the relationship between 1 and 3 in the first scenario is 1 is strictly less than 3. But the middle scenario is equally plausible. It could be as you see here, 1 and 2 overlap, 2 and 3 overlap, and that 1 and 3 actually meet. So it's also plausible that they meet. The third scenario has, again, 1 overlapping with 2, 2 overlapping with 3, and the relationship between 1 and 3 is overlap itself. So now we have a kind of operation where you're taking overlaps combined with overlap, and the result is not a single relationship, it is a kind of triplet. It's a disjunction of these 3 possible outcomes. So it's not like arithmetic where 3 plus 5 gives you 8, okay? And nothing else. Of course, if you did modular arithmetic, it would give you multiple answers. Well, so here it's giving you multiple answers, and imagine a nice table, call it a multiplication table or whatever, where you look on the top and you find overlaps of these 13 different relations, you find overlap, and in here, you find overlap composed with overlap, gives you not a single relationship, but these 3. The other ones are inconsistent. When I say that one is one of these 3 relations with 3, it means that the other relations, like bigger than, are inconsistent.
What does overlap mean in this context?
In this
It seems to be an asymmetric relationship.
Yeah. So here are what I mean by these relations. So overlaps, X overlaps Y, O. I really mean this picture, that X really starts, and then Y starts, and X finishes, and Y finishes. And if I do overlap to the -1, I mean Y is overlapped by X, and it's just the opposite. Okay. And similarly, before means this relation, meets sharing, during or includes. This is during, this is finishes, this is equivalent. So there are, in Allen's temporal algebra, these 13 different relationships between intervals. Here is another way of looking at those 13. It's called the numerical lattice. It's just a hierarchy of what the intervals would be if you were to, say, shift one of the endpoints a little bit to the right, or I guess, going down, it's shifting it to, shifting the Y a little bit to the left. If you shifted this one here, you would get to this. If you shifted this endpoint a little bit to the right, you would get this relationship. Okay, so this is the 13 relations of Allen, and so the semantics here is that we do not know the precise relationship between intervals, but it must be one of the relations in some set of possible relations between X and Y. So I'm looking at interval X, interval Y, and each one will have a kind of domain of what are the possible relationships between them. It might be that we have no information, in which case all 13 relations could be still valid. As we get more information, we might be able to reduce the size of the domain XY. In computer science, we have something that's known as the satisfiability problem. You usual satisfiability problem from logic, from one of the NP completeness problems that you study in algorithms. There, in that usual satisfiability problem, you have variables that can take either a true or false value, 1 or 0, and you have constraints binding them. Usually they are disjunctive normal form or conjunctive normal form. We have terms where you might say that x1 and x2 and x5 bar has to be true, and you take a disjunction of those, and you ask whether a certain set of true and false values give you a true statement or a false statement. In reasoning in AI, we have a slightly more general kind of scenario, kind of problem called constraint satisfiability problems. So it's satisfiability, but using a more general kind of constraint. So let me just tell you what this is, because it's relevant for reasoning about these intervals. So in CSPs, in general, you have variables which are, well, we could say Rij for all possible pairs of intervals. So a variable is not the interval itself, it's pairs of intervals. Okay. So Rij would be talking about the pair of interval I, interval j. And each of the values of that variable will be some possible values from these 13 relations. And making a connection with the usual satisfiability problem that you're used to. And that, you have variables, say, x's with values taken from true, false. Here I have variables with double indices, indices, which can take values from 13 possible values. And the domains will be disjunctions of current possibilities, meaning that the domain of Ij will be all of those possible 13 relations that are still consistent with the information that I have so far. Then, to reason about further information that isn't given to you by the data is done by this algebraic closure. Look up in my big calculation table, like overlaps gives me less than meets over. And the propagation of constraints, meaning once I use my rule once to, say, make the domain of possibilities smaller, that might then imply that I can make some other domain smaller. And there's a kind of chain reaction. That is what propagation means. It's a chain reaction. Now, 13 relations are a lot. And so in my research, I looked to see whether or not we could somehow make this a little bit simpler than all the possible 2 to the power 13 disjunctions. Because if I have 13 possible relations, every pair could be some disjunction of it. There are 2 to the 13, which is a big number, possible domains that I could have. So we decided to introduce some macros. Sure.
And you didn't want to simplify it by assuming that everything will be endpoints on a line, and then just for every interval go in and just trim as points, and each interval gets its own additional.
Right. So one possible simplification would be to go to point events instead of intervals. If you go to points and you talk about the point algebra, Then you have a whole system of reasoning, only about points. It does make it simpler, and you'll see that what I'm going to show here will make it something similar to that. But point algebras tend to have much simpler algorithms associated with them. And if you let me go on for 2 hours, I could talk about those too, but I'm not going to. But let's say in a whole series of talks, I would give like one talk on point algebras and simple temporal problems. I prefer to talk about, I'm talking about the intervals because they are closer to the research that I've done. But you'll see the simplification almost immediately. So the simplification that we will be looking at is that of the 13 possible relations, if I were to combine starts, finishes, during, meets, overlaps, equivalent, and their inferences into one relation called intersection. So these 11 get combined into a macro called intersection. Then, in fact, we would only have 3 relations. Namely, intersect, strictly less than, strictly greater than. That's a little bit different than if I were talking about points. Because in points, you would have less than, greater than, or equal. And there's a qualitative difference between equals and intersects. So now if I'm looking at the disjunctions of only 3 elements, they would be that I know that it's just the singleton less than, the singleton greater, the singleton intersect, or less than intersect, or intersect greater than, or less than greater than, or all possible, all 3, which means don't know, meaning that all 3 relations are possible. So from now on, when I'm going to be talking about 3 relations, we'll call it the interval algebra on 3 relations, A3. And there are 7 possible disjunctions. So I need to give you an example of how this simplifies things. And an example will be the story of Goldie and the 4 bears, which of course all of you know. Once upon a time, there were 4 bears: Papa Bear, Mama Bear, Baby Bear, and Teddy Bear. Each bear sat at a table to eat his morning porridge, but since there were only 2 chairs, the 3rd chair was broken in the previous story, the bears had to take turns eating. Baby and Teddy always ate together, sharing the same chair. And on this day, Mama was seated for part of Baby Bear's meal, when the door opened and in walked their new neighbor, Goldie. Here I have a story. I have temporal clues. I have information about only 2 chairs. I have information that Baby and Teddy always sit together. I have information about that there was some point in time when Mama was seated at the other chair, and the door opened and in came Goldie. So here we have Mama seated at the table, Baby and Teddy seated at the table, and in walks Goldie. That's what a great aroma, Goldie said. Can I join you for a bowl? Mama replied, sure, but you'll have to wait for a chair. Yeah, I know all about chairs, said Goldie. So Goldie sat down when Baby and Teddy got up. See the temporal clue? Baby and Teddy get up. Goldie sits down. So Goldie is now sitting down. Mama presumably stayed in her place. And in walks Papa to the kitchen and looking at Mama, he says, I wouldn't sit at the same table with that girl. Mama answered, then it's a good thing you ate already. Another temporal clue. So some of the questions you may ask if you are a detective on CSI Miami. Not CSI New York or Las Vegas. Would be, could Papa and Baby both be seated at the table together? Could that have happened? Could it have happened? Yes. Could it have happened? Could Papa and Mama both be seated at the table together? No. That could have happened too. Could Papa have spent some time at the table with both Baby and Mama? Probably not. Did anyone sit at the table with Goldie? Well, according to the picture, yes. And according to Papa's statement, I wouldn't be sitting there, implies that she was sitting. So there are some facts from the story. There are only two chairs, that's spatial information. We know that the interval when Baby was sitting at the table and Mama intersect. This is temporal information. We know that Baby is strictly less than Goldie, because of the statement, Goldie sat down when Baby got up. Papa ate before Goldie, because that's a clue from the story. Mama intersected with Goldie because of Papa's statement. And so I can draw a graph labeled by this temporal information. I have a node for each interval, and the edge indicates what the relationship between those relationship intervals are. So, okay, so I can't go backwards unless I go. Okay, we were, the information, remember, so this edge, Mama, Baby, has intersect on it. That was the only piece of information we know. This edge between Papa and Mama could be all possible. We have no information. Similarly, I've written on each of these edges what the possible relationships are according to those facts that I gathered. And now, I use some propagation technique. Okay, and what am I using? Less than implies less than. If I is strictly less than J is strictly less than K, then in my table, and just common sense, I is strictly less than K. This would be one kind of relationship. Here is another kind of relationship. If I is less than J, and J intersects K, then the possible scenario would require that I is either less than or intersects K, but it's impossible for I to be greater than K. That is, of the relationships between I and J, there is no K down here. That allows me, on this edge, to eliminate the circled relationship. So my table deletes some of the impossibilities. So in general, this is what we would do. We would have a graph like this with all of the information. Then we would run the propagation with our table to try to eliminate some of those. You do this all of the time. When you play Sudoku, what do? You're looking at a box and you're saying, okay, right now, according to what I see from my game, the numbers that could be in this box are 1, 3, or 7. And then you look at your constraints and you say, I can eliminate 7 because there's already a 7 in a row, so you zap that from your possibilities. And the domain reduces and reduces. We're doing the same kind of thing. We are reducing the number of possible values. In general, that's what you do in constraint satisfiability problems. You have a propagation phase where you're reducing, and then after that you have some kind of exhaustive or maybe heuristic search. So we're interested, as sort of theoreticians, in what is the complexity of testing whether the information that you get is consistent. We proved that in general, this interval satisfiability problem in A3 is NP-complete. And as a result, as a corollary, one gets the NP-completeness of the same problem for 13 relations, which had been proven with very ugly proof. In 86, it also had a mistake in it. It was finally fixed 3 years later. But our proof goes for A3, and then you get the other as a corollary. Okay, fine, NP completeness. But, in fact, sometimes you're very lucky. Sometimes you're lucky that your constraint problem is constrained sufficiently that you can use the fact that certain domains can't possibly happen in order to take advantage of that extra information to solve problems efficiently. That's a kind of meta statement. And for that, we introduced something called fragments. So you could ask, what if not all possible 2 to the 13 relations happen for Allen's algebra? That only some of those interval relations are actually used in your story. Could that help you in solving it efficiently? Okay. So, for example, the fragment of singletons in A13, meaning that each domain is just a single relation, no disjunctions at all. Well, it's known that if that were the case, that you had the information between each pair ij was exactly told to you, then you could check to see whether it was consistent in polynomial time. In the regular stat version, it would be like if you were told the value of each variable, true or false, then you can just evaluate the possibility to see if it is true or false. Let's look at, however, let's look at our coarser algebra A13. So it's complexity of testing fragments in A3. So some of the fragments turn out to remain polynomial, to remain NP-complete. One of those would be this. Even if all you were allowed to say about the relationship between interval I and interval j was intersect or disjoint, meaning less than or greater than, disjoint, intersect or disjoint, or don't know. If that was your language for expressing the information from your story, the problem would still remain NP-complete. Or if your language was somewhat different, you were allowed the disjunction less than intersect greater than, or disjunction, then Weber, a couple years later, proved that was also NP-complete. However, there are fragments which are tractable. So the problem turns out to be linear if the input disjunctions are the singletons, this doubleton, or don't care. What's missing? Of the 7 disjunctions, what's missing? disjoint. So of the 7 relationships, if your problem doesn't use disjointness, only uses these 6, then suddenly the problem becomes solvable in linear time.
Just to be clear, we're talking about, we have intervals, and then we are told for each pair of intervals, or for some pair of intervals, or for each pair of intervals?
Let's say each pair of intervals,
Each
because
pair-
if you're told nothing about them, then it's don't know.
Okay, and for each pair of intervals, you're given a label, and you say, okay, can all that be true? Is there a set of intervals?
Right, exactly.
Can I ask one
Yeah.
question? So is there sort of Schaeffer-like result, sort of dichotomy result? You know, in the 70s, the Schaeffer showed that for satisfiability problem. If you have this relation, one of these relations is NP-complete, otherwise polynomial intractable. In your sort of interval algebra,
Yeah.
if you have say this set of equations, then it's NP-complete. Otherwise, it's polynomial.
Right,
I
so-
I was wondering, but it's a kind
Okay,
of
so
something.
this slide actually answers that.
Ah,
About what we would normally call dichotomies in
Mhm.
people. So what I've done is I've given these 2 situations that are NP complete. Now I've given this as being linear, okay? But there are other collections that do have disjointness in it. For example, this 1, 2, 3, 4, these 4 possible disjunctions is also linear. And if the only other remaining combinations that are not subsumed by smaller collections would be this one, less than, greater than, intersect, and disjoint. And this has an n-cubed algorithm. So in some sense, this is what we often call a dichotomy, where if you can find a place where it's sort of like above it is NP complete and below it is polynomial. So this actually characterizes exactly what the situation is for all possible combinations of domains for A13. Why is this important? With everything I learned about solving constraint problems, I could even say in the past 6 years, I've learned from Sudoku. I always think of that as a standard example of CSP. But what are the advantages of tractable fragments? The use of tractable fragments, it could be useful in testing partial solutions. Like suppose I have this graph and they're labeled, and okay, if I'm lucky and my labels all go into one of those 3 categories that I can solve fast, great, I'll solve it. But if not, then I might just look at a subset of the vertices and their labels, where those labels actually do fit into one of my fast classes. So I'll run the propagation and the fast algorithm only on that subset. That'll be good because that'll cut down the number of labels for that subset. Then I might take another subset that also had good labels and run it there. So I can use that as sort of subroutines to test partial solutions. And of course, if I take part of it and I get a contradiction, meaning that it's not satisfiable, then the whole thing is not satisfiable. If it is satisfiable, then I sort of continue. So it's a guide to generating choices in global search. It's a kind of good heuristic to use. And if I order the variables wisely, as one tries to do in general for CSPs, using fancy algorithms like partial look-ahead and so on that you would study in lectures on CSP, then that also can speed things up. So this simply reiterates a little bit more in that case where I take the relations but not disjoint. Okay? The way I prove a linear time algorithm will be to translate relationships between intervals into relationships on their endpoints. So, Bert, right?
Yeah.
So, when you asked about points, when interval I is strictly less than interval j, then I know that its right in closing it, point is less than its left. And if this was a relation, I would know that the left is less than or equal to the right. I could translate intersected into either this or this, similarly here. So in this case, I'm able to translate the interval relations into relations on its points, and then I can solve it using Rothschild or Dijkstra or one of those guys. This is the translation, and then I can I basically create from these a bipartite graph, and I run a topological. In fact, I don't even need fancy algorithms. It's enough to take a topological sort of this bipartite graph. So I won't explain this since we're down to the last 5 minutes or so. Just tell you that one can translate these to a bipartite graph, test using topological sort. Everybody here knows topological sort, right? And that is sufficient to test consistency. People have tried the same thing for all of A13, and using other fragments, something called the Horn algebra that uses about 11% of the disjunctions, and they can do that, but none of those include disjoints. So people talked about that. Are there more? Well, yes. There's 17 more maximal tractable subalgebras. That's a lot of work to find that. And then in 2003, there was a complete list. So if you want dichotomies, you got it. A complete list of all the maximal tractable subalgebras, and there are, I don't know, about 20 something of them. And to do that, you need computer-assisted proofs. So then my friend Bert Schwery, her answer to what was important for temporal reasoning was, well, I like the problem where you have this library, and person A arrived between 10 o'clock and 11, person B arrived before A and left after the library and went for lunch. Other people were coming and leaving, give a bunch of data of who comes into the library, when do they leave, and mixtures of information. At the end of the day, a book was missing. So they called in CSI Miami, who stole the book.
The assumption is theft had to have occurred while the librarian was at lunch. Is that the?
Not necessarily. Not necessarily. There are various assumptions you would make. Most of the time is that you make the assumption that if two people were in the library at the same time, at least one of them saw each other. And she remembered that story as coming from somewhere, and she said, I can't tell where, don't remember, but the students always enjoy it. So I said, well, actually you read it on page 20 of my book, but in fact it goes back to problem that was posed by the Hungarian mathematician Hoyos in 1957 about going through people seeing each other in some common place. And in fact, what she saw in my book was what is called the Berge mystery story. Claude Berge was a very famous French mathematician, combinatorialist, graph theorist, and he coined this mystery story. 6 professors had been in the library on the day that the rare tractate was stolen. Here are the assumptions. Each one had entered once, stayed for some time, and then left. So we're talking about intervals of time. If 2 were in the library at the same time, then at least one of them saw the other. Detectives questioned the professors and gathered testimony, temporal information. And here's some facts. Abe said that he saw Bert and Eddie. Bert reported he saw Abe and Ida, etc., etc. One of the professors lied. Who was it? Well, it wasn't Claude Berge. Usually what I do, sometimes in my class, I stop here, I say, okay, and I leave the room for 5 minutes, and somebody has to come back and tell me who stole the book, who lied. All right? Claude was a very special guy. He was a sculptor. He was an author of regular literature. He loved hex and chess. And he actually used that Berge mystery story later on to create a story that was published in a French literature magazine. So here's the solution to that problem. The problem sets out with a sort of a testimony graph of who said that he saw whom, and you find certain inconsistencies like this cycle. And that's because intervals on a line cannot have chordless cycles like that. And you can read the solution someplace else, but it turns out that when you have something that's inconsistent, it must be that your liar is among the 4 people on that 4 cycle. So you can eliminate, send people home, and you end up with 2 possibilities, and then you have to argue further, again, about the properties of time intervals on the line. Well, was Desmond so stupid, or was he ignorant? But had he studied algorithm graph theory, he would have known that his testimony wouldn't have held up, and he would have adjusted his answer accordingly. It appears in lots of different books, and so on. It has to do with reasoning about intervals on the line, and problems about scheduling classrooms, which I can skip. So let me just conclude by saying that Claude Berge is quoted as saying the use of mathematical tools may be unexpected. And you never know when that can help you in your reasoning about time intervals or other reasoning problems. So thank you very much. That's one of his sculptures. And that's his chessboard. I don't see where his go board is.
Well, this might be a bit, so when you had that idea, you had the relationship Rij, and there's 13 values for each, so 13 possible relationships. Can you recast that to Rijk, where k is run from 1 to 13, and cast it as a set problem? You add in some natural constraints like overlap is inconsistent with disjoint, and then reduce it to a set problem, and then do a set problem?
I would think so.
I would imagine that a set solver could solve very large problems. You don't worry about the blow-up quite so much.
Right.
Compared to constraint set factors.
Yeah. So I don't know whether you would just translate into a SAT problem and just take a thing, or some people like that work specifically on the temporal might have like a a special solver for it.
The reason why I asked was Sudoku is trivial. That's
Anything else? Okay, so those of you who've only written up 4 out of the 5 talks, I guess this is required material.
Thank you.
And for those that have already passed in your 5 required ones, thank you for your attention. Anyhow.